Welcome to our presentation. My name is Sujeong and my partner Joshua will present our final project entitled Collision Avoidance for Multi- and Trailers Vehicles using Probability Map-based Waypoint Sampling. The problem we are dealing with is how to operate a multi-USV with a sensor array without collision. Since we have to consider a long sensor array, these structures have a high risk of collision. To approximate the sonar array, we used end-trailer dynamics. We composed our algorithm using several theories including end-trailer Dobbins dynamics, prioritized trajectory generation, probability map-based waypoint sampling, and collision checking. Each component will be explained in details in the next several slides. The trajectory for every agent is generated using end-trailer dynamics depending on the priority values of the vehicles. We propose an approach based on prioritized trajectory generation, which considers the distance of the vehicle's planning domain. Before planning the trajectory, first, algorithm calculates a distance heuristic using normal Dobbins dynamics for the head component of the vehicle to generate the heuristic vector of all vehicles. In the initial condition, the algorithm only considers static obstacles in environments. Then it performs the trajectory planning in iteration, starting with a vehicle with the lowest distance heuristic and continuing with a vehicle with a higher heuristic. Every time the algorithm successfully generates a collision-free trajectory for a vehicle, the algorithm will then append the generated trajectory as a dynamic obstacle for the following vehicle's trajectory planning. Thus, trajectory planning of the last vehicle will have the maximum number of obstacles that need to be considered.
So Dobbins dynamics is a simplified version of the car-like vehicle dynamics. It is notated by x dot equals v cos theta 0, y dot equals v sinus cos theta 0, and theta dot equals to u, which is the input control to the vehicle. In Dobbins dynamics, we define 6 maneuvers called LRL, RLL, and so on, where L equals the left turn, R is the right turn, and S is a straight movement of vehicle. In Dobbin dynamics, we consider that the input control to the vehicle is constant, and the vehicle turns with constant turning radius. And next is the end trailer dynamics. It consists of several components. The first one is the head. We assume that the head dynamics will follow the car-like dynamics, which already explained before, and the dynamics of the trailers are explained by these equations on the bottom side of the presentation. Based on the two dynamics explained before, we proposed a new dynamics called end-trailer Dobbin dynamics that will generate the trajectory of every components in the end-trailer vehicles from the initial location to the goal. The steps that are required is first we need to calculate the Dobbin path for the head component of our end-trailer vehicle, and then we need to integrate the trailer dynamics with constant input along every segment of Dobbin's path. For example, in the figure on the left, there are 3 segments. The first is turning right segment, going straight segment, and turning left segments. And in this slide, I will show you how do we generate the trajectory using our proposed algorithm. First, we need to check the feasibility of generated path with direct path from initial to the goal. If the generated trajectory is not feasible, we are going to do the waypoint sampling using the probability map, which will be explained in the next slide. After we put the new waypoint into our environment, we will check the trajectory generated from the initial to the waypoint. After that, we will also check the visibility from the waypoint into the goal. If then the generated trajectory is invisible, we will need to also sample another waypoint until we get visible trajectory both from initial to waypoint and waypoint to the end goal.
The idea of waypoint selection comes from the fact that it should be far from both the initial location and the destination, assuming a direct trajectory between both is invisible. However, we also need to consider the total distance objective of the trajectory planning algorithm. Thus, we need to search the area between the initial and destination, possibly around the middle section, while still allowing exploration in other regions when no solution can be found. We then derive the probability as the negative potential function. We define two types of potential function to achieve this behavior: attractive potential UATT and repulsive potential UREP. For the attractive function, two types of distance functions are commonly used, which is quadratic and linear, and also called the conic. The quadratic function considers the distance as a square norm function, and the conic function considers the distance as a norm function. Both functions have their advantages and disadvantages. For example, the quadratic function can highly penalize points far from the middle section Qm. However, it poorly defines the potential values in area close to the middle point. On the other hand, the conic function can precisely define the potential value around the region of interest because it is based on proportional function. However, it weakly penalizes points located very far from the middle points. To combine the advantages both quadratic and conic functions, the conic parabolic function is used by switching both the quadratic and conic functions based on the threshold value Qz. To address the obstacle in the probability map, a repulsive function is used. The repulsive function is based on a switching function that only activates on a region closer than a distance boundary d0.
As explained before, in the trajectory generation, we need to check for the collision between the agents and the obstacles. So we propose the collision checking based on the polygon intersection. The steps includes: first, we need to define the polygons for every obstacles, including the static obstacles and the dynamic obstacles. After that, we can use any available algorithms to detect any intersection between pair of polygons, such as sweep line, rotating calipers, or Gilbert-Johnson-Kirti distance algorithms. And then finally, we are going to make the simulation to test our proposed algorithm. First, we generated 3 test scenarios. In the first scenario, we generated a single agent and a static obstacle. The agents are required to move behind the obstacle to reach its destination. And then in the second scenario, we generated 2 agents which they are required to switch their location. And then in the third scenario, we are generating 4 agents facing with each other, and the objective is to switch the location of the front-facing agents. And this is the result for the scenario 1. In the figure is shown that agent 1 can successfully generate the trajectory from its initial location to the end location without any collision with the obstacle. And this is the result of the scenario 2. We have 2 agents, agent 1 and agent 2. Because of the prioritized trajectory generation, agent 1 will consider our obstacle-free environment, so it will just generate trajectory directly from initial to the goal position. But after that, in the second iteration, agent 2 must consider the collision avoidance with the agent 1, so it will need to take a detour until it reaches its final destination. And this is the result for the scenario 3. Similar with the scenario 2, the first agent will just take a straight path from its initial position to the final, and the other agents will need to consider other agents' path, generated path, as the obstacles. So this is the resulting trajectories for every agent.
Finally, we are concluding our works. We present a collision avoidance method for multi- and trailless vehicles using probability map-based waypoint sampling. The trajectory planning consists of two main components. First, the algorithm calculates the priority list by calculating the distance heuristic using collision-free Durbin's dynamics for the head component of the vehicles. Then, the trajectory for every agent is generated using our proposed end-to-end Durbin's dynamics step by step, depending on the priority values of the vehicles. With the prioritized trajectory generation method, the generated solution does not guarantee optimality because we only consider the objective of the individual agent at every trajectory generation step. However, we can generate the trajectory of multi- and trailless vehicles quickly. The probability map-based sampling method is proposed to select appropriate waypoints using the potential field function. We propose the probability map such that probability in the middle section between initial and destination is high, while allowing exploration in other regions when there are no feasible solutions. In future work, we plan to extend our probability function to consider the continuous domain, considering the dynamics obstacle such as sensor coverage and the real-time recursive function for the dynamic obstacle.